Hello, Honors Algebra 2. Today we will be doing our 6.2 notes since I am unable to be in class tomorrow. So these shouldn't take too terribly long, but you are going to need your graphing calculator, so go ahead and pull that out. We're going to start with the definition of a polynomial function. So this is our very lengthy looking definition, and that's standard form for a polynomial function. We always want it in descending order, which means we want the largest exponent first. Alright, so we have degree of a polynomial function, and that gives us our highest exponent. When our degree is 0, we call that constant. Basically, that's when your function does not have a x term. So it could look something like this. Or that 3 could very well be a -2. Essentially, this is a horizontal line. Okay, no x value, that's why our degree is 0, because our highest exponent is 0. Okay, because this is the same as x to the 0. Next is linear. This is your line that we have dealt with before. It's where your highest exponent is a 1, and that's something like this. Highest exponent of 2 is quadratic. That's when you have an x squared. So like the things we were dealing with in our last chapter. And I'm just coming up with random numbers here to show a quadratic. A degree of 3 is called cubic. That's when you have an x cubed. And just because you have an x cubed doesn't mean you also need a squared, an x, and a number. You could have some of those or, all of them. It doesn't really matter. We'll make this a minus. 4, when our highest degree is 4, it is called quartic. Okay, so highest exponent is a 4. Just come up with something here. And the last one you need to know is a degree of 5, and that is quintic. That's when your highest exponent is a 5. Make it interesting. There. Alright, so how do you know if you have a polynomial function? Well, first of all of your exponents have to be whole numbers. Okay, so meaning no negatives and no fractions. And all your coefficients have to be real numbers. So real numbers as in no imaginary. So we are going to decide whether the function is a polynomial. If it is, we're going to write the function in standard form and state its degree, type, and leading coefficient. This first one here, if you look, it has an exponent that's a negative. So that means this is not a polynomial function. However, the second one is a polynomial function. Our exponents are all whole numbers, and our coefficients are all real numbers. Now remember, an imaginary number is a negative underneath a square root. This is just a negative number. That's absolutely fine. So now we are going to put this into standard form. That means the x to the 4th is going to come first because it has the highest exponent. And then we'll just go in descending order. So it would look like this. The degree is the highest exponent, which is 4. The type is the name that goes with that exponent, which is quartic. And the leading coefficient is the number in front once we are in standard form, which is a 1. Now, when we evaluate a polynomial function, we've actually done this multiple ways before. One way is to put it into your calculator as an expression. So that's literally plugging x in into your calculator. We also had function notation. That's where you go to your y equals and you type your function into y1. And then remember we did our vars, y vars, function, y1 of, and you could put like whatever you needed. Okay, and you get a value. We also have trace on our graph. We usually use value. So if you had something in your calculator and you graphed it, you could do second trace value and choose that 2, and that gives you the same answer I got before. And this one, put into y1 and set your table to ask. If you go to your table set, so second window, right now you have independent and dependent variable at auto. What you can do is change your independent variable, which is your x, to ask, and then basically it's the same thing as your value that we use on our graph. Alright, so using one of these 3 methods, because these are the ones we've used most frequently, you're welcome to do the last one if you'd like. I'd like you to go ahead and evaluate this function right here for x equals -2. Again, you're welcome to just plug it in, to use function notation, to plug it in and do value on your graph, or you could try this table method. Okay, give it a second and try it. Alright, so what you should have gotten was an answer of -92, and that is by simply plugging -2 in. Now, when you do this, be careful because there is a negative there, so make sure you have parentheses around it. Okay, so if you were able to type it in exactly like this, you should get a -92 for any of these methods as well. Alright, next is end behavior. So end behavior refers to what happens to the function as x approaches positive or negative infinity. So let's take a look at our first graph right here. Please type it in with me. You'll probably be done before I am. Alright, so if I take a look at this, it looks like, sorry about that, we had a little issue, but we are back. So here we go, I have drawn my graph here. And go ahead and sketch something similar to this on your paper as well. And what we're going to do is describe the end behavior. So when you do end behavior, it's always going to start off like this. As x approaches positive infinity, f of x approaches, and then we're going to figure out what goes in the blank here. And as x approaches negative infinity, f of x approaches, and then we're going to figure out what goes in the blank there. Now you don't actually have to draw the blanks, but this is how it's always going to look, and then we have to figure out what goes in the end. So as x approaches positive infinity, that means as we are going to the right, as x approaches positive infinity, what's happening to the actual curve, f of x? Or you can think about what's happening to the y-coordinate. Well, as we go to the right, this y-coordinate is going up. And because of that, it is approaching positive infinity. As x approaches negative infinity, so that's as we go to the left. What's happening to the graph? Well, hey, it's still going up. So f of x is also approaching positive infinity. Alright, just to save some time, I want you to pause the video, take a second, and type this second one into your calculator. Alright, welcome back. So, you should have had a graph that looked something like this. Maybe not perfect, but something along those lines. For your end behavior, always start the same. As x approaches positive infinity, f of x approaches, and as x approaches negative infinity, f of x approaches. So again, as x approaches positive infinity, that means as we're going to the right, what is happening to the curve? And what's happening to the curve is it's going up, so it's approaching positive infinity. As x approaches negative infinity, we are going to the left. And what's happening to the curve as we go to the left? It's going downward. So approaches negative infinity. And there you go. That's how you do end behavior. Now, it turns out that this next part is a little hard to explain just over a video. So what we're going to do is this bottom part, or excuse me, this middle part here, we are going to go ahead and we're going to talk about that on Monday. It's not something that you need to memorize, it's just going to be easier to talk about in person. So we're going to skip down to our final problem. We're going to graph the polynomial and describe its end behavior, and your graph should contain all of the important information, y-intercept, x-intercepts, and all local mins and maxes. Alright, so I want you to take a second and get this typed into your calculator, and then we'll be back in just a second. Alright, so here you go. This is the graph that you should have in your calculator. If you don't, go back and check that you typed everything in correctly. So I'm just going to go ahead and do a brief sketch of that. It helps if you make this sketch really big because we are going to put a lot of information on it. Okay, so something like this. Okay, so it said label the y-intercept, x-intercepts, and all local mins and maxes. Okay, so this is an intercept, an x-intercept. This is a local max, and we call that a local max because it's a max in the general region. But this also has a local min right here. And then we also have a y-intercept. Okay, so these are the 4 points that we're going to need to find. We also need to do our end behavior, which we can do right now. As x approaches infinity, f of x approaches, so I'm talking about as I go to the right, what's happening? It is going up. So it approaches positive infinity. As x approaches negative infinity, so that's going to the left, what is f of x doing? It's going downward, so approaching negative infinity. Okay, here is my end behavior. Alright, now let's go ahead and find all of this information. So make sure you have an equals 0 and y2. That will make finding our x-intercept easier. Second trace 5, enter, enter, enter. Nearest thousandth, as always, please, negative 2.757. Comma 0. For our y-intercept, I'll do value. X is 0. Oops, it went away, but it looked like 0, 3. To find your local max, you're going to go ahead and find this the same way as always. Second trace 4 for max. You're going to go to the left of the max. 1 enter. To the right of the max. 1 enter. And then you're going to go right in the middle. So negative 1.549, comma 5.631. Okay, and then we just have to find the min, and we'll do that in a similar fashion. We will go to minimum, and you want to be to the left of the min. And to the right of the min, and then basically where the min is. So 0.215, comma 2.887. Make sure you get the same thing, please. And there you go. All right, so we will finish this part on Monday. Make sure you remind me so I don't forget. And we also have notes on Monday, and then we review on Tuesday, and you have a quiz on Wednesday. All right, have a great weekend. Bye-bye.